the amount of money spent by recycling centers. So if the items are already sorted out, we predict that it takes less time for them to process all the material, thus reducing the amount of cost for energy used in the plants and money spent on hourly wages. And the other thing we wanted to do is make sure it's only powered by batteries, so it's easy to place it wherever you want in the city or any location. Next.
Okay, let's have some quick view first. This is the major test module of our project. This is top view of the entrance. This is the distribution level. This is the testing level. Okay, this is a flowchart of our project. Basically, sort one kind of bottle at a time, and finally it can transfer 4 different kind of bottle into 4 different bins. First, I want to introduce pressure sensor and infrared sensor. In our project, infrared sensor is used to wake up the whole system, and the pressure sensor activates every test procedure.
This is what a metal detector works, and this one is a metal detector we choose. The working voltage of this one is 5.5 volts, and it can only detect 4 millimeters. Although it can only detect 4 millimeters, we can use the step motor to move forward, and then it will always touch the bottle to measure it. And then we compared this with some other metal detectors, such as we used as screening check. Those ones looks like can detect in a longer distance, and it is more powerful to detect the metal. But if we put that one in our rubbish bin, it will have more space for we will have less space for some other parts, and we should it always need more energy to work. The working voltage of some other metal detector is more larger than this one. Since our rubbish bin is standing straight, so we need to use a smaller one to save energy.
According to the research, the weight of most empty glass bottles are more than 0.5 pounds. So we tested the apple juice bottle, which is 0.62 pounds, and is the lightest one we can find in the market. The result of the pressure sensor is 283 grams. In addition, we also tested the bottles made of plastic, paper, and metal, and the results are all less than 100 grams. So if the result of the pressure sensor is over 100 grams, we assume it's glass bottle.
We use the distance sensor to determine the plastic bottle and paper bottle, because the plastic bottle is more physical resistance when squeezed. So we use the step motor to squeeze the bottle, and the distance sensor will keep tracking the distance. If the step motor doesn't push all the way, then it is a plastic bottle, else it is paper bottle.
So this level is detecting level, and I will explain this how the sorting level works. So for example, if we want the bottle to fall into these bins, we rotate this board about 30 degrees, so it will directly fall into this bin. And if we want the bottle fall into this bin, we will first rotate this board to about 90 degrees, and this to 30 degrees. The bottle will fall in this board, and then it come back to its original position. So the bottle will fall into this bin. Vice versa, the bottles can fall into all the 4 bins.
So the biggest thing we changed from the midterm is we also added 2 power modes. In the original design, we also expected there to be a solar panel and a charger circuit, but we didn't have the budget or the time to implement that. But what is implemented is we have 2 Arduinos. The first Arduino, it takes care of the general testing of all materials, and the second Arduino is what monitors the power of the battery and signals the first Arduino which modes to go into. So the two modes, there's a regular operation mode where the pressure sensor is waiting for 10 minutes, we programmed for 10 seconds. Waiting for 10 minutes for a bottle. If it does not see anything, then it goes into a sleep mode, which is woken up by these infrared detectors placed in the middle of the tube. The second mode is just a deep sleep mode, where when it is activated, it immediately returns to deep sleep and does not remain in normal mode for what would be ideally 10 minutes or half an hour in the real world, but in this case, just 10 seconds. Next. So we took some measurements on what the power consumption is if we threw in 10 objects with a 5-second delay between each object. And what we found is for plastic and metal, the average watt hours are about the same, 72 to 75. And that's because the motion is pretty simple. The stepper motor is moving forward and moving back after some distance. Whereas, go to the next slide. In the paper test, there's slightly more power being used because now it's moving the maximum distance. It's not seeing any physical resistance from paper cup. Now, these.
So what is so you drop in paper 5 seconds apart.
Yeah.
And you average the energy, and that's what you report as the
And
power. Okay.
that's what we report as the power under extreme conditions.
Busy.
Yeah, and and during a party, there's somebody always throwing something out. And yeah, so these are over the extreme conditions. As you can see, when it is in sleep mode, in all tests, it only every second it only uses about 2.3 watts, and when it is testing, it uses about 16 watts for each test. Okay, so we're going to demonstrate it. These are the quadrants which each material should go into. And it's cooperating. That's good. So right now I just calibrated. First, let's start with the paper.
Flame machine.
It's
Expected, or it's like almost dying?
No, it's not the sturdiest design. As you can see, it's pretty much a skeleton.
No, as long as it is
Yeah.
normal, then.
Now the speed of each test, the longest it takes for paper was about 20 seconds. The quickest is obviously glass. It just weighs the object and it knows this is a glass object. Okay, so what happened is that was a failed test because it bounced, and so it didn't register that over 100 grams. And so through those 10 instant tests that we did, we saw a 10% failure rate. On another day, we also ran it 20 times for each, and again, it was the same 10% failure rate. Another interesting thing we noticed is when it does fail, it assumes the object is plastic. So all the failed bottles go into the plastic bin. So let's say at the end of the day, what we would see as an efficiency is the plastic bin has, let's say, 50% plastic and 50% everything else, whereas the other three bins are always 100% metal, 100% glass, or 100% paper.
So you can also like get the plastic bin out at the end of the day and then toss it in.
Yeah, you
do another
exactly.
footprint.
So, I mean, as for overall efficiency, I don't want to say it's 75% accurate, but it's pretty accurate since 3 out of the 4 bins are always at 100%. Yep. There's a few more slides, real quick.
Next is budget.
Yeah, to build this, this is pretty much the expected parts, give or take a few items, and we spent just for this about $150, $160. Obviously, there was extra parts we had to buy to replace things and whatnot. And then I think
The whole construction is at testing mostly items from hardware store, right? Nothing fancy in there. That's good.
And then, you know, this stuff is actually recycled. I found it in the hallway. A few other recycled parts in there. So, you know, stick with the theme.
That's good. All right. Any questions? No? All right, very good. Yeah, thank you.
Just had one. Okay, I'll talk about it.
You picked up all the morning ones, right? So I'll pick up stuff from you, the double ones.
Just, yeah.
我看手机。好。